Now, the next operation we want to apply on this branch is to tilt the branch basically on the Y global axis. So right now we do have something like this, that it quickly flatten out. And what we want to do is basically apply some, let's call it gravity, to the branches in a way that the lower one, which are the thicker one, they will tilt toward the ground, let's say, so something like this. It will be some minimal variation, something like this for the middle one. For the upper one, which are lighter, we want to tilt it toward the sky, so something like this. And to do that, we basically just need to further rotate the direction vector. Now we are in a flat plane, so basically we can use the global y-axis to perform a rotation. So basically, if the green one is our current direction, let's say this is the positive y-axis, we can calculate a cross product between the two of those, and that will give us a vector like this that we can basically use as an hinge to rotate this new direction vector, up or down. So, back inside the triangle, let's duplicate the flat one and put it right after the flat. Let's call this one tilt. And here, delete everything inside the condition, but keep the condition because it will work the same. And also the ramp. We need a ramp to filter out this tilting only after a certain age is reached. So for this one, we actually want to do something like this. So in this way, we make sure that no tilt is applied until they are flat to the y-axis. And since we are going to need a minimum and a maximum angle, as well some perturbation range, might as well go back into the init attribute and let's copy these 4 lines here. So back into the solver on the tilt node, and let's compute it before the condition. So let's pass it right here and delete the base line. We don't need this one. So actually here we want to do the reverse. So first the perturbation range, which we can set it to something like, I don't know, 5 degrees, or rather 10, because remember we are multiplying a minus 0.5 to 0.5 range, so the maximum and minimum angle will be actually half this value. And this is just the value that will be added to the minimum and maximum angle. So here CHF angle min plus pert, and same for the max. Basically, we want to set this angle. Let's set it to minus 20 for the minimum and 30 for the maximum. So this is to say we want to apply minus 20 to the lower branches and 30 to the higher one. So basically we can use the Y position to modulate this value, which we can see is roughly going from 3 to 15. So basically here, let's create a new float variable. We will call this ref y. And here, let's fit, for now, let's just plug the y position. After the branch logic, we will need to compute another kind of position, but for the time being, let's say that this is fine. So y position from 3 to 15, and we want to fit it from 0 to 1. So now we have a normalized position from 0 to 1, and we can use it to compute the final angle. So float angle is equal to fit 0, 1. We want to fit the ref y, and we want to fit it between the angle min and angle max. So this is outputting basically a range from minus 20 to 30, and we want to multiply all of this for the age ramp. So we are not tilting the branches until this age is reached, so by age. So now that we have the angle, let me go inside the condition. We can perform our rotation. We said we want to perform the rotation on the cross product between the direction vector and the y-axis. So let's compute a vector variable, vector cross. It will be equal to the cross product between the direction vector and the y-axis, so set 0, 1, 0. Then with this axis and the angle, we're going to compute a quaternion. So vector for quat is equal to quaternion function. The angle is angle and the axis is the cross one. And we need to make this angle in radians as usual. Too many parentheses. And this should be already normalized, but just to make sure, let's throw a normalize in there. So now we can actually compute the new direction, so new dir, qrotate function using the quat we created, and the vector we want to modify is the current direction. Let me make some space. So now we can update the actual attribute. So be at dir, new dir. And let's check it from this side. As you can see, the lower branch are going toward this angle plus this perturbation range, and the upper one are going toward this angle. Now, we still miss a few things to add for our direction, but before doing that, I want to address the branching logic, because it's becoming boring to see only the main branches. And basically, the whole idea behind the branching logic is that, let's say we have this branch growing. We want to establish some distance that will trigger the branching. So this point is traveling, and when it will reach a certain distance, it will generate another branch. That distance will be tied to the mass we are carrying over the points. So basically, more thick is a branch, and more distance it needs to generate a new branch. And let's say here we reach the distance trigger for the first time. A new branch will be generated and a few things will happen. Some of those on the new point and some of those on the original point. So first off, we will need to decide a new angle. So this branch, let's say it will open like this. And in response, we also want to use that angle, the inverse actually, to modify the direction of the original one. So this is the first operation. Then the original point will lose some mass, and this will make that the branch, as it lose mass, it basically generate more branch because it needs less distance, and we will also use that mass so in a way that when we have less than x mass, we will stop the growing effect. So basically, a new angle, both for the new point and for the original one, a new mass, because the original one will lose one, and the new one we will need some mass, because it doesn't have one yet. And also we will need to establish some ID value for the new branch, otherwise we will have problems with the add node. So, back inside the solver, let's make some room between the move and the trail. That's where we want the branch to happen. And let's drop down another point wrangle. We will call this branch, make it, I don't know, pink. And here, let me just copy the per angle min, angle max, because we want to use it also over here. And create the channel. So we want to set the perturbation range to 20, the angle min to 45, and the angle max to 60. Basically, we will use some random factor to open the new branch from 45 to 60 plus the perturbation range based on the mass of the branch. So this is the channel we need for now. And also, if we need to calculate a distance, we basically need a reference position. Now, we want to calculate the reference position considering the point where we start for the main branch, but let's say if a branch will be generated here, the new reference for this new branch needs to be the points where it has been generated. I hope it makes sense. So this is to say, let's go back outside for a second, and here on the init let's also initialize another vector attribute. We'll call this ref p is equal to the current position, at least for the initial point. So basically this position won't change. So the branch is growing, and its reference to measure this distance will be the position, where it has born. So back inside the solver, on the branch wrangle, let's retrieve this position and bind it to a variable. So vector ref p is equal to v at ref p. And now we want to create the distance to check. So first of all, the threshold, so float threshold, it will be equal to a float parameter, so chf, let's call it trigger distance, and we want to scale it by the mass, so multiplied by f at mass. And now we need the actual measure, so float this. We will use the distance function from the current point position to the ref p. So the position, I keep mistaking myself, the position where the point has been born. And now for the condition, let's copy this line from the trail. Here we want to paste it, and we are good to checking if the frame is every each frame, but we don't want to check if the frame is greater than 1. Rather, we want to check if the distance, the measured one from the position to the reference position, is greater than the threshold, so threshold. And basically this threshold, let's create the parameter here. If we set it to 2, basically it will be 2 on the lower point that has a mass of 1, and it will scale accordingly until it reaches the minimum mass, which currently is 0.6 on the highest point. So let's close the condition. And when this condition is met, meaning when the distance is triggered, what we want to do is to add another point. So let's create an integer pt, add point function, geometry 0, add the current position. And now, as soon as we generate a new point, we need to change this distance, because, I mean, not the distance, but the reference position, because otherwise, if the points keeps moving and the reference position always stays the initial one, as you can see, here we do have 2 points overlapping because it will keep branching every time the solver will cook. So let's make some comment here. This will be the space reserved for the new point attribute, and this will be the one for the original point. So on the original point, first we want to update the ref position with the current position, meaning at the frame where the branch will be generated. So just by doing this, we should solve the branching issue. Let's see, let's check it from outside. We have 1, 2, 2, 2. No, we didn't solve it. Let's see. We need to carry over this on the trail, of course. So duplicate this line, paste it, and we want to carry over the ref p, which is the v at ref p. So hopefully now we should have the duplicated point only every now and then. Yeah, one is here, then 1, 1, 1, and there is another one. So it's working. Now we said that when the point will branch, we will lose some mass. So here let's compute a float variable. We'll call it new mass, and it will be equal to the current mass, and we will subtract 1/5 from the current mass. So f at mass divided by 5. This is just some simplified value that I found working for this kind of setup. Of course, you can change this, you will have a different result. And now we want to assign this new mass to the original point. So f at mass is equal new mass. This by itself won't do nothing because there's nothing in the solver yet that is saying when you reach a certain mass, stop growing. So we want to compute that next. And we want to drop down another point wrangle after the trail. This will be the last wrangle and it will deal with the stop of the point. So we want to make the same color as the move because this will is a moving thing. And in here, let's copy the, where it is the condition, usual as frame greater than 1 and modulus of 5. We want to check the mass. So if we nest another condition basically, so the if at mass is less than a channel, we will call this stop, then we will remove the point entirely, the current point. So 0 at ptnum. Close the if and the outer if. And what did I miss? A parenthesis here. And let's say if the mass will be less than 0.2 maybe, the points will stop. And of course, always on the moving group. So let's reset the cache and let's see if they stop. And they did. As you can see, the lower one, they will start with a higher mass of 1. They will stop, they will grow more than the upper one, which they start with 0.6 of mass. Now, back on the branching, we established that the point has been created. So now we need to move the new point to the moving group, and we need to assign to that point the new direction. So we also need to calculate that direction. Before doing that, let's make some room up here and just create a new integer variable. We will call this count, and we will retrieve an attribute called count that it doesn't exist yet, but I will explain it very soon. And inside the condition, the first thing we want to do is to increase this count variable. So count plus or equal 1. Basically, we need this count because similarly like we did on the trunk, where each point would rotate by that golden angle, and we use that combined with the point number. Now we can't rely anymore on the point number, but we need to do the same rotation on the branch, meaning if the first branch will go toward the left, we can open the next branch to the same direction. We want to apply that golden angle rotation, and this count will provide a counter similarly like the point number did on the trunk, because the first branch will be 0, then the second branch will be 1, and so on. And the concept of what we're going to do is the same as before. Basically, we will rotate the direction to open the branch from its parent, but first we want to rotate the subvector for that golden angle. So the angle that we want to open the direction will be based on the thickness, similarly to the trunk, where the thicker branches would open more compared to the thinner one. So here, after the count, let's compute a float variable. Let's call it B angle, like bend angle, I don't know. And we want to fit the mass, which we know is going from 0.6 to 1. And we want to fit it from this angle mean and angle max. So angle mean, angle max. So now that we have the angle, we can create a quaternion with it and the axis that we already have. So vector 4, let's call this quat up because we will need another one for the direction. So quaternion, and this time let's explicitly hardcode the golden angle. So radians 137.5 multiplied by the count plus the perturbation range, And basically all of this is the angle of rotation, and the axis to rotate is the direction. So now the QRotate function, so vector the new up will be QRotate. We will use the quad up we just created, and we want to update the up vector, so something like this. We don't see anything because we need to assign this new vector to the new generated point. So first, let's set the point group to assign this new point to the moving one. So 0, moving, pt, 1, and set. And for the attribute, let's set point attrib 0, the up on the pt, the new up, and we will set this value. So now we should have, yeah, as you can see, the new point is not moving yet because we are not passing the direction vector, so it doesn't know where to move. But as you can see, when it has been generated, it gets the new up, which I don't think is taking correctly the golden angle. Let me check why is that. And this doesn't work for two reasons. The first one is that here we are retrieving the attribute within a variable, and we are increasing the variable, but we need to actually bind this count to this attribute we are retrieving here for this to work. So e at count is equal to count outside the if condition, and also we need to pass this count attribute to the trail wrangle. So here let's say count e at count. So now let's reset everything. We should see the rotation on the up vector, and we do see it. As you can see, the first branch will go here, the second here, and so on. Now with this new vector, we can actually rotate the direction with the usual quaternion function. We have the angle, which is the B angle, and the vector is the new up we just calculated. So after the new up, let's make another quaternion, vector for quat dir, quaternion function. And this time we want to rotate in radians always. The B angle we computed up here, which is based on the mass and the two parameters, and the axis is the new up. Let's close the parentheses here. Now the final vector for the direction, so new dir, qrotate function, rotate the quad dir, and the axis we want to, the vector we want to update is the current direction, so v at dir. Now we need to assign this vector to the point, so let's copy this line, set point attrib, and set the new direction attribute using the new direction value. And now the point should move at least for a second. And they don't, they have the correct direction. Let's see what they miss. I mean, they miss a lot of stuff, but they should be moving at least for one count. Right, we are not assigning any mass, so the mass will be 0, and for the condition is them to stop when the mass is less than 0.2. So let's also transfer the mass, and this should be enough for the at least the initial movement. And we want to assign to that the new mass we computed over here. So now they're moving, and of course something weird is happening because they are branching right away in a weird way because we are not updating the ref position. So for this point, the trigger distance will be always the original one. So we need to compute another ref position. So copy this line, paste it, and this time we want to assign the ref p attribute, but we want to assign the current position. So each branch will consider the position where it has been born as the reference position. And now we do have something which makes more sense. Of course, when they lose enough mass, they will stop. But if we go on the add node, we will see a marvelous thing here. And as you may imagine, this is because our ID is all messed up now. I'm not even sure we are carrying over the trail. Yes, we are. But either way, we need to compute some new ID for the branch. Otherwise, we can't connect them individually as polylines. So back on the branch wrangle, let's set it before the mass. We want to compute a new ID, which currently is a string value. So string new ID. We want to take the current ID, which is basically something like, where is it? Branch 0 and so on. And we want to append other numbers to it. So basically we want to add to the string, when you do an addition on a string is basically a concatenation, so it's not a per se addition. We want to add an underscore and then the current count number, so I to A count. And we want to set it as the ID attribute. So new ID. This won't produce, the cleanest ID attribute in the world because it will be somewhat messed up, as you can see, but you can always enumerate those. And more importantly, is more than enough to tell this branch apart. As you can see now, we are on the add node and we have the correct connection on the branches. So back inside the solver, for the new point, meaning for the branch, we almost done. We just need one more attribute, which is the birth frame, because we need that to calculate the age. So copy one final time this line, and we want to set the birth attribute with the current frame as the value. So now we have a correct age computing on the branches too. What we miss now is the update on the direction of the original branch. We say that when the branch is generated and it's rotate, we want to compensate also on the original branch with maybe a fraction of this rotation on the opposite side. Right now we're just growing toward the original direction. So back on the branch wrangle, we updated the mass and the reference position. We want to update the direction with the usual quaternion stuff. So on the original PT space we made down here, we want to compute a new quaternion. We will call this O for original quat dir, and let's not start with the capital letter. Some people get angry when you did it. And we use the quaternion function radians. We want to rotate on the negative of the B angle we created, let's say divided by 3, so 1/3 of that angle in the opposite direction. And the axis is the new up, because we calculated all the things with the new up vector. So down here, we want to update the direction vector. Let's do the rotate function right into the assigning part. So O quat dir, and the vector to update is the direction one. So now we should have the rotation. Yeah, as you can see, it's not heavy as this one. It's just 1/3, but it is happening. Basically, the original branch are changing direction also.